Hello. Hi, everyone. Welcome to our AWS Hugging Face workshop on how to accelerate BERT inference. We are going to wait a few more minutes until people will join. Maybe what's quite interesting for me would be to know where are you currently and have you used SageMaker before? People are typing Atlanta. Awesome. Yes, nice. That's great to hear. Yes.
Brazil.
Wow.
Istanbul.
Chicago, India.
Colombia, cool.
That's a lot of messages. Spain, Mumbai, DC. Wow.
Wow.
Well, what time is it currently in India? Isn't it like already 11 in the evening or something?
10:30, I guess.
Yeah. 9:30. Wow.
Or 9:30, yeah.
Wow, so thank you for being so dedicated. I'm not sure I would want to listen to SageMaker talks at 9:30 at night.
Midnight in Singapore.
That's crazy. Yeah, so we are going to record the event and we'll publish it to the Hugging Face YouTube account afterwards. So if you cannot like listen the full hour or need to like move to another meeting or have something else to do, you can like easily look up what we have done on YouTube or also like do it a second time. Wow, Chile, 12 p.m. Yeah, we will share the YouTube link on social media and in the forum. So just keep an eye on it and you will find it.
Should we share the forum link now, Philip? Or?
Yeah, I think, yeah, you can share that already.
Right.
So for those who have worked with Hugging Face before and maybe for the new ones, so we have a nice big community forum where you can like ask all tons of questions about Amazon SageMaker, Hugging Face, about the things we will do in the workshop, also about things we are not doing in the workshop, just out of curiosity. You can like ask us anything. Lewis should send a link anytime soon. Yeah, there it is. Awesome. I think, yeah, let's wait 2 more minutes for people to chime in. We are already at 218, which is like super crazy.
Amazing. Thank you everyone for coming. Exciting time.
Working late now in India.
Yeah, Carlos, it's going to be recorded and shared on the Hugging Face YouTube channel.
So 1 more minute. Last chance for people to get started. Yeah, no SageMaker. Yeah, it's not that much important if you have SageMaker experience or not. This workshop is not mostly about SageMaker. It's also about like how to work with Hugging Face transformers, how to apply knowledge distillation, and we will use SageMaker in the exam, like in the workshop, to deploy a model to SageMaker for real-time inference, where you can send your requests to the model. But yeah, I think you can easily get through the workshop without much SageMaker experience. And if you afterwards like to get more, like to know more about SageMaker, we have done a few more workshops in the past to get it started. You can also find them on the GitHub repository we will share in a minute and on YouTube.
Yes, we will be taking questions at the end, but you can just leave any questions in the chat, and also we'll interrupt each other.
Yeah, and Søren, yeah, maybe in the future there will be something for GCP, but currently I have no idea what the future will bring. So hopefully, who knows? And yeah, so I think we can get started. So welcome again for everyone who joins from India, Singapore to US and Europe. And today we will focus on how to accelerate BERT inference with knowledge distillation and AWS Inferentia. And me joining is Louis, who is a machine learning engineer and also the author of the newly Transformers book, Natural Language Processing with Transformers, and also joined by AWS is Heiko, who is an AI/ML solution, senior solution architect. And I'm Philip, I'm a technical lead at Hugging Face. So welcome from our side. And what we are going to do, so the workshop consists out of 3 different labs. The first lab is fine-tuning a large transformer model with Amazon SageMaker. We are going to skip this part since we only have 75 minutes and want to really focus on the knowledge distillation and acceleration part with AWS Neuron, but you can like rerun the training with SageMaker after the workshop or tomorrow or whenever you have time. Lab 2 will be making models smaller with knowledge distillation. This will be a deep dive by Louis, really showing you, okay, how can I apply knowledge distillation to transformer models? How would I select my teacher? How can I select my student? Or what's really important to look after for doing knowledge distillation? And lab 3 will be the hands-on part where you will get access to temporary AWS accounts and where we will convert a Hugging Face transformer model with the AWS Neuron Sdk and then deploy it to SageMaker for real-time inference, achieving super low latency. And what this means in terms of numbers, we will basically lab 1 fine-tunes a BERT-large model on the Clink OOS dataset, which is an intent classification dataset, achieving 79% accuracy. Then we will distill it to a MiniLM, achieving 94% accuracy. And then we will convert and compile it to AWS Neuron, which will still be close to 94% accuracy. And in terms of latency numbers, we will go from over 300 milliseconds to 6 milliseconds per inference on a sequence length of 128. Also, for you to get help, we have a huge Discord. You can join it. You can ask questions about Hugging Face, about transformers. You can share ideas, projects. We also have the forum, which Louis already shared. And then there's the GitHub repository where all of the code for the workshop will be stored. You can open issues if you have questions, and we are happy to help you. Okay, first of all, I'll hand over to Heiko, who will give you a high-level overview about Amazon AI and SageMaker.
All right. Let me just share my screen. Right. You able to see my screen? Excellent. Hi and welcome everyone. This is going to be brief. I don't want to bore you too much with slides, but just a very brief overview of SageMaker and what it is. And I like always to think about it starting from the machine learning lifecycle, meaning you start at the top with accessing your data, cleaning your data, and then preparing your data. Then you build models, which you then train and evaluate. You deploy a model, you monitor it. At some point, you find out, you have some model drift, and that means the whole cycle starts again because you might have new data, which you have to clean, prepare, train your model, and deploy again. And that's basically what we're trying to do here at AWS with SageMaker, to give you a suite of tools that lets you do all these steps within one machine learning platform. So as you can see on the top, we have the different stages again: preparing, building, training, and deploying your models. And then in the columns, you have the different services that we offer within SageMaker to help you get do all these things within the machine learning lifecycle. So today, for example, we're going to be focusing, Lewis is going to be focusing on training models, and then in the hands-on session with Philip, we're going to be deploying models to a real-time endpoint in SageMaker. And speaking of the deployment, just a quick overview on AWS Inferentia and these Inf1 instances that Amazon has developed for machine learning inference. They're not GPU instances. GPU instances are usually mostly not the right instances for inference. Oftentimes, if you aim to use GPU instances, they're most of the time underutilized, and that's why AWS created this Inferentia chip with a much lower cost and higher or lower latency as well. And the idea here is really that you have these neuron cores on the chip, and the neuron core is the custom accelerator, and each Inferentia chip comes with 4 of those neuron cores, and that enables you then to either load one model on each core, or for higher throughput, or one model across all cores for lower latency. In terms of what that looks like then with performance and cost is that we have up to 2.74 times higher throughput than the G4 GPU instances on AWS. Also, we are delivering those inferences with a cost savings of up to 68% compared, for example, to the G5 instances. That's really it from my side, just to give you a brief overview of like what we're going to be covering today.
The question we had from the chat is, how does an Inferentia deployment cost compare to deploying on an AWS Lambda now that there's a 10 gigabyte accessible storage layer?
So different use cases we have. If I can I quickly go back to the slide where I have the deployments on the right-hand column in SageMaker? There's different use cases. So we have multi-model endpoints, we have real-time endpoints, we have asynchronous, and we also have serverless endpoints. And there are different use cases for each one of those. Up until recently, the serverless endpoints that are based on Lambda, those were primarily used for smaller models where you have infrequent inference requests, whereas Inferentia you would use in a scenario in an application where you need super low latency real-time inference requests and lots of them at the same time. So and then you have asynchronous, which is again for a different use case. It's where you need near real-time inference, but the inference sometimes, because these language models can get really large, inference can sometimes take a minute or two, and when it's not critical that you have it in like a millisecond, then that's where we recommend the asynchronous endpoint. So it's not like you can compare them apples to apples, if that makes sense. You always got to think about what is your use case, and do I need what do I want to prioritize? Low latency, accuracy, cost, and so on. There's no one size fits all. Hope that makes sense.
Great. Again, then we can get started with our deep dive on how to do knowledge distillation. We will try to answer all of your questions either like directly with the person who is like currently doing the session, or answering in the chat. We definitely won't skip any question you ask. And to quickly answer Kritika's question is, can we use Inferentia to deploy on fine-tuned transformer model? Yes, we can, and that's basically what we are going to do later.
Awesome, thanks. So basically what I'm going to do here is try to give you a kind of high-level picture of what knowledge distillation is and how we can actually implement this for transformers using SageMaker. So in the next sessions, I think Heike will show you how to set up AWS SageMaker. But basically, all of this is coming from this really nice GitHub repository that Philip has created for SageMaker. And we're working in workshop 4, where we have these 3 different labs. So lab 1, we're not going to go through today, but this is basically where we train a large Roberta model. And then in lab 2, which is what I'm going to cover, this is where we actually take this large model and we compress it into a smaller model. And lab 3 is what Philip is going to show us later, where we take that compressed model and then we apply these fancy optimization techniques with Inferentia, and we get some much nicer compression and speed. Okay, so I'm not going to show you how to clone the repo and set up your SageMaker account. But basically, once you do that, you'll end up with a kind of Jupyter instance like this, where you'll see these 3 notebooks. And so if you click on the knowledge distillation notebook, you'll get something like this, which has a bunch of text that explains how this works, and we'll go through that together. But at this stage, what I want to sort of just tell you is for knowledge distillation, the main concept is that we have kind of 2 models. There's a teacher model, which is the large model, which is a very high-performing model. And we have a student model, which is typically much smaller. And that's the thing that we want to somehow give the information from the teacher and make it perform better than just if we fine-tune the student from scratch. So the kind of picture that you typically see is that you have these 2 models kind of working in tandem, and you have a way of kind of measuring how well the student is able to kind of mimic the predictions of the teacher. And I'll go in these details in a bit. But what I just wanted to say is just this is the cartoon, we'll go into it. And the code itself is relatively simple, especially in SageMaker. So the main thing you need to do is just install some basic packages that we need. And then what we're going to do in this notebook is we're actually going to push the models that we train with knowledge distillation to the Hugging Face hub under your account. So if you don't have a Hugging Face account, you just can go to hf.co or huggingface.co, and then you can sign up. And once you have an account, you'll get something like this, which is kind of like a feed of different activity. And when you want to basically provide credentials to SageMaker so that it can associate the model that you've trained to your account, you just need to basically hit this notebook login cell and provide a token. Now, these tokens are pretty similar to other platforms. You basically have tokens that control what you can read and write from. And you'll find your tokens under your user account if you go basically on this little profile icon, go to settings. And here, if you go down to access tokens, you can basically pick an existing token, or you can also just create a new token if you want. So here I've got a token that I have for workshops. So I'm just going to copy that by clicking here. And then when I feed this into this little widget, it will then authenticate my SageMaker instance so that then anything that I basically train, I can then push to my account. Okay, so I'm just going to go through this code very quickly, and then we'll go back to the kind of theory and the concepts, just because it takes around 10 minutes to sort of train the model. So here there's a little bit of configuration associated with SageMaker, which is just going to tell us something about this session that we're running, and in particular, which kind of S3 bucket we're going to be using to ultimately store the model to. So this, if you've never seen SageMaker, this is kind of just some boilerplate that just allows us to kind of configure the session for the current role we have. And so here you can see, you know, I have some Amazon role, we're on this bucket on US East, and we're in this region. So this will be different when you're running this with the hashes that we provide for you. But in general, it's just some basic boilerplate. Okay, so I'll skip this for now and come back to it in a sec. Now, the basic thing that I was mentioning for knowledge distillation is we have a teacher model and a student model, and we're going to somehow take the knowledge of the teacher and compress it into the student. So here's a model that we've trained earlier, which is this BERT-large fine-tuned model on a particular data set. And the kind of use case that we thought would be interesting to showcase today is something called intent classification. And intent classification is a kind of text classification where you're trying to basically understand if a snippet of text is revealing some specific intent from a user. So the data set that we've used for this is called the Clink 150 data set. And this is a data set where you've basically got text that represents kind of like the type of queries you might get in a chatbot. And so the idea is like, imagine that I type into some app, what is my balance? Then the classifier has to work out, okay, I'm asking about balance. This is probably something about an account. And then you can provide, you know, some information about that account. But the problem is that, like, if you've ever built a chatbot or anything that's kind of conversational, you know that like there are these kind of like turns in the conversation where people may ask things that are completely out of scope. So you can see in this example here that after asking, you know, what is my balance, someone might say, oh, how are my sports teams doing? And here, if your model has never seen an intent that represents anything about sport, it may get basically confused and just give you some kind of garbage result that, okay, you know, something about your payday. So this data set is kind of interesting. It basically has a whole list of intents. There's 150 different intents. And it also has out of scope intents, which means that, you know, doing well in this data set for these models is often quite tricky because you need to be able to predict things that you haven't really seen. And you can find this data set on the hub. It's called Clink_OOS. And you can see here some examples of, like, you know, can you walk me through setting up direct deposits? And I guess these are all direct deposit, but I'll let you, I'll put this in the chat and, you know, you can have a look and see what the data that we're dealing with. Okay, so that's the task. So text classification or intent classification. And we've already trained this BERT-large model, which I'll also share here. And this BERT-large model gets quite good performance on this data set. It gets an accuracy of around 97%, and the classes are roughly balanced, so that's not such a misleading score. And this is the kind of situation that you'll typically experience in industry, where if you want to really maximize for performance, you'll typically pick a large model because, you know, the larger models have more capacity, they typically score higher. But then if you say, okay, now I want to deploy this model into a production setting, I kind of have a problem because these large models will typically take, you know, several hundreds of milliseconds to generate a prediction. And if you're building a kind of application that has these you know, dialogues between a customer and your chatbot, then this is, you know, far too slow for the average user. So what we're going to do is we're going to take this large model and we're going to basically compress it into a smaller model. And the model that we've picked today is a variant of what's called MiniLM. So basically, if you're using the Hugging Face Hub, almost everyone is using kind of BERT or DistillBERT. And these models are generally great for starting with, but obviously the field evolves over time. And MiniLM is really probably, you know, the state-of-the-art model in terms of doing something fast and getting good results. So it's kind of like DistillBERT, but, you know, a little bit better. And this particular model is a pre-trained checkpoint. So this is a model that one of our colleagues at Hugging Face has actually distilled himself using a technique we'll mention in a sec from a BERT-large model. But at this stage, it's only a pre-trained model. So it has no head that represents text classification. And in particular, it has no knowledge about this Clink intent classification data set. So what we need to do is basically do a form of fine tuning, but during the fine tuning process, we're going to augment the signal that comes from the labels of the data set with another signal that's coming from the teacher, which is this BERT-large model. Okay, so basically that's what I've done here. I've just got these two hyperparameters, which say which is my teacher checkpoint, which is my student checkpoint. Here we've specified what is the data set that we're dealing with. So this particular data set has a bunch of different subsets, and I've picked one called the plus subset, which just has a few more of these out of scope examples. And then we're going to train for 10 epochs, and we've picked, there are a couple of hyperparameters, which I'll explain shortly. One of them is called the temperature, which if you're familiar with generative modeling, that's a pretty common one. And there's another one called alpha, which I'll explain shortly. And we kind of figured out which parameters were good doing some hyperparameter optimization previously. But later you can also run your own optimization if you want to find different values, for example, if you're using different models. And then we have some kind of key arguments that we provide. So push to hub here, we'll say, okay, at the end of my training, I want to push this model to the Hugging Face hub. And in particular, this is the ID that I will expect to see this model under my account. And we have a job name for SageMaker. And basically, then that's it. We just now have this Hugging Face estimator object. So if you're not familiar with SageMaker, if it's the first time you're seeing this, you can think of this as very similar to the trainer in Transformers. It's kind of just a wrapper around all of the logic that we need for training. But it has some like extra things that we can configure. For example, we can specify what instance type we want to do our training on. We can specify what Transformers version, what PyTorch version, Python versions. We can also specify a script that will be executed on that instance. So this is really kind of like a meta trainer because the actual training itself will be inside this script. And we'll go through that logic shortly. So I'm just going to run this. And then once you've basically configured your Hugging Face estimator, you don't have to really do much except run Hugging Face estimator.fit. And there's the main parameter you need to maybe think about is weight, whether this is true or false. So if we set this parameter to true, it will basically store all the logs in the notebook itself. So this is kind of closer to the experience that you may have from coding in notebooks generally. But what I'm going to do is I'm going to set it to false because it actually will store in the logs my token on the hub. And then, suddenly you can basically get access to all of my repositories, and I don't want that to happen. So I'm just going to run this. And what this has done now, we're using at the moment a SageMaker instance, which has only got a CPU. But what we've done is we've now launched a job on a GPU machine. So one of these P3 2x large machines. And you can inspect these trainings by going to your SageMaker console. And then you'll see in the training jobs here, we've now launched a new knowledge distillation job. And this is in progress at the moment. So this is now going to take probably 10 minutes or so to run. And so what I'm going to do now is I'm actually going to explain how knowledge distillation works and some of the sort of technical details of what's really happening under the hood. But before I do that, are there any questions right now?
Yes, there's a question by Ottomana. I hope I pronounced it correctly. Where a few already also asked the same question. Are we like using a distilled model and distilling it again, or are we fine-tuning the distilled MiniLM model?
Yeah, that's a great question. So I think the way to answer that is with a picture. And this will be a nice kind of segue into what we're going to cover. So when we talk about knowledge distillation, as I mentioned at the very start, there's this concept of two models. There's a teacher model, which is typically the big model, and a student, which is the smaller model. And there are kind of two different ways that people traditionally convert or transfer the knowledge. So if you're doing something called task-specific distillation, which is what we're doing today, the basic idea is that you have this teacher, you have a student, and at the start, this teacher is already fine-tuned on the task that you care about. So this is, for example, the Roberta model that I showed you before that it's been fine-tuned on Clink. And then what we do is we take a student model that is just a pre-trained model, and then we're going to do fine-tuning with this distillation signal. So it's kind of like the standard fine-tuning that you do all the time, but we have an additional signal coming from the teacher, which I'll show you shortly how that works. Now, in this particular case, we chose for the student a model which is called MiniLM, blah, 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 distilled from BERT-large. So this is actually already a distilled model, kind of like DistillBERT. But the way this was created was using what's called task agnostic distillation. So the idea here is you take a teacher model and you have a student, and you basically just do the distillation procedure as part of your pre-training. So at this stage, there's no concept of task-specific heads. You're just doing pre-training. And that's a slightly different type of distillation that we won't do today, but it's often the one that produces many of the models that you'll see on the hub, like DistillBERT and MiniLM. And we just picked this particular MiniLM variant because it's already quite small and quite fast. So that has like the kind of properties that we want to start with.
Another question from Giovanni is, should a teacher and a student share the same architecture?
Yeah, that's a great question. So I'm going to share a link, or I'll put this in the chat. So basically, there's a fantastic paper by Microsoft called Fast Formers, and they did a very extensive analysis of knowledge distillation. And what they point out is that in their experiments, distillation typically doesn't work when the teacher and the student have basically different architectures or different vocabularies is probably the better way of putting it. So they find out, for example, if you take Roberta as your teacher and Bert as your student, that doesn't really work. And then, of course, this would also apply to other things like, you know, if you take something like, I don't know, Big Bird and you try to distill it into a very different type of student, like maybe Tiny Bert, it will probably not work. But I'm kind of skipping ahead of many details. So I think what I'll do is at this stage, I'll sort of, let's take a step back and ask ourselves, like, you know, what is this knowledge distillation all about and how does it work? So the kind of cartoon that we can use is that we need to find a way during training to provide information to the student about the knowledge that the teacher has acquired during its own training, right? So, for example, here we've got a teacher, which let's suppose it was already trained on some form of like classification. So here, you know, you've got 4 classes to classify maybe different reviews of food. And so the idea is that we've got examples like the tacos were okay. We know the ground truth, which could be meh. And we also know that the teacher, which has already been trained on this type of data, it will make a prediction for what it thinks is the most likely label or you know, class for that particular example. So the way this works is we during training, we basically augment the standard cross-entropy loss that the student has with an additional loss term, which is called the knowledge distillation loss. And this additional loss term, what it does is it basically compares how good are the distribution of probabilities from the teacher matching the distribution of probabilities of the student. And the idea is that you want the student to somehow mimic the teacher over time. So at the start, the student basically knows nothing about the task. It's just kind of like randomly initialized. But during training and through backpropagation, hopefully then the student will learn that, the teacher is telling me that, okay, for this particular set of examples, here are the class distribution, or here are the distribution of class probabilities. I should essentially adapt my own predictions to kind of match that. And the way that matching is done is using something called the KL divergence. So the KL divergence is this kind of like, let's say, scary mathematical thing. But basically what you can see in this equation here is it's just taking essentially the difference of 2 probability distributions, P and Q, and it's got some logarithms in there to make it kind of behave nice. But the basic idea is that if you have these 2 distributions, P and Q, one for the student, one for the teacher, then we can include this comparison in the loss. And the thing that we typically do in the field is we say, okay, we're going to include this loss term, and then we're going to essentially have a weighting where we have the standard cross-entropy loss plus this knowledge distillation loss. And the way we weight this is usually with a parameter called alpha. So if alpha is 1, then we basically switch off knowledge distillation completely. And if alpha is 0, then we completely switch off all the signal coming from the cross-entropy. And in practice, some kind of balance between the two is typically what you're looking for. And this is a hyperparameter that you can optimize for. Okay, so we've got these like two loss terms. And the one thing I haven't quite mentioned yet is what is this like this T parameter or this temperature. So the reason we have temperature in the picture here is that if we imagine like what kind of distribution the teacher probabilities will be for my examples, what you'll typically find is that if the teacher is really good, because it's a big high-performing model, then those probabilities are going to be really highly peaked around the true value. So you can see what I mean if we look up here. Here on the left-hand side, I have what is basically like the ground truth. So we see that meh is getting all the probability, and if my teacher is a very good model, it will then assign a very high probability to that class and very low probability to the rest. And then the student basically learns nothing new from the ground truth labels. And so that doesn't really help us very much. So what people have done in literature is they say, okay, let's try to kind of smoothen out the distribution of probabilities from the teacher by using this temperature parameter. And the temperature parameter is basically a normalization factor that is applied to the logits of the teacher. So the idea is that when I'm computing my probabilities, I usually apply a softmax function to my logits. But before I apply the softmax, I can just divide my logits by a parameter called T. And then if I control and tweak this T parameter, it will basically kind of smoothen out the probabilities. So you can see in this kind of cartoon here, now that I've set my T equal to 1, this might be kind of like what the teacher typically would predict for this particular example. So, meh is still highly peaked and the others have less. But if I start cranking up this T parameter, then I'm going to kind of smoothen out the probabilities and assign a greater weight to the kind of rarer classes. And the idea is that this T parameter is, again, another hyperparameter that we can tune for. And as we increase T, the student will then have to kind of make or do a greater effort at trying to mimic this kind of more flattened distribution. And then this, ultimately may help us, get a kind of more robust and better performing model. Are there any questions at this stage, Philip?
Yeah, there are quite a lot of questions with this, which is awesome. Raj asked, like, I think a pretty complex question. Maybe we can quickly tackle it to give some pointers. But he asked how to distill an encoder-decoder architecture than just an encoder architecture, and how he could implement it with the hiding face trainer.
Yeah, that's a really good question. So if we look at this cartoon here, what you can see is that it's very much representing like an encoder type setup, because we've got essentially a classification task. So the loss here for the task is cross entropy. Now, what you could try to do if you're doing like a sequence to sequence model, the question is basically what should you change here for this loss term? So if you imagine that I'm doing something like I don't know, let's say maybe translation or summarization, then what I'm basically trying to do in the training phase is I'm trying to basically predict what is, for example, the one shifted example in my text. So if I've got my let's say my long text, and then I want to predict my summary, I've kind of got like a way of scoring that using a particular loss term. So if you change your loss term to be whatever it should be for sequence to sequence tasks, then the rest of the process will in principle still work. Although I personally haven't distilled any sequence to sequence models, so I don't know if it really does work, but I think it should.
One of the most common questions also in the chat is like, is there any intuition that you can quickly give on like why distillation is better than just taking a small model and fine-tune it on the data set?
Yeah, great question. So The simple answer is that the loss term that we're dealing with is this L student, and this is a mix of two loss functions. So it has a standard cross entropy, and it has this additional knowledge distillation term from the teacher. So the kind of intuition that one sees in the research literature is that if we just ignore the teacher entirely, so we switch off this loss term, then we're just doing standard fine tuning, right? But if we start introducing this additional loss term from the teacher and we make it have a greater weight than the standard cross entropy, we're actually providing a way to give the model some sort of like additional information about the kind of decision boundaries that exist, in the particular data set. So what I mean by that is when you just have very hard targets, ground truth, you just got one possible class and nothing else. The model basically has to learn over time what these decision boundaries should look like. And, in general, these decision boundaries are like, kind of like smooth things in multidimensional space. But we have to learn that from very hard examples, like, just zeros and ones everywhere else. Sorry, 1 and 0 everywhere else. So it takes more steps to learn that, typically. But if we have a teacher which has already learned what these decision boundaries kind of are, then it can actually provide this kind of smooth information through this knowledge distillation loss. And so the kind of intuition is that we're kind of giving the student a kind of like head start in understanding what the decision boundaries are kind of really are. And it doesn't have to do all the hard work of learning that just from the ground truth. But it's a very good question. Okay, so I'm just going to have a quick look to see if our model is still training. Okay, so it's still in progress. And if we look at the training job, yep, we can see it's still training. So one of the cool things actually is that during training, we're actually going to produce checkpoints, right? So as we train, we're going to train for 10 epochs, and at each epoch, we're actually going to push the checkpoint to the hub. And so the cool thing is on the hub is you can kind of see how your model is doing in real time, because we've now got this checkpoint, which is essentially the distilled student. And if you click on metrics, we'll be able to see now on TensorBoard, how is the accuracy doing? So you can see, for example, that at this stage, the accuracy is like around 82%, maybe a little bit more. And we know that the teacher started off with like 97% accuracy. So, at the moment, we still are quite a long way away from the teacher, but hopefully by the end of this training, we'll be a fair bit closer. So this is all basically comes automatically with the trainer and transformers. We have a TensorBoard log callback, which will automatically log your training. And this then means that you can inspect, how the loss is performing. And what is the button that lets me kind of scroll this way? Yeah. Okay, so now we're at like around 87. The other thing that's actually kind of fun is in the middle of training, you can play with the widget for your model. Okay, well, the demo gods are against me. Usually you can play with the model during training. And this is actually kind of fun because this gives you a way of seeing like, if I give the model some kind of tricky examples, do I see kind of qualitatively how it gets better over time? Okay, so let's just see. This is still training. So yeah, let's see. Are there any questions?
Yeah, I think there are a few questions, but since we have like 30 minutes left, maybe Heiko can get started with handing out the AWS accounts to everyone to not be able to like see how the knowledge distillation model work, also that we can compile it to Inferentia and deploy it to SageMaker.
Yeah, that'd be awesome.
And while that, I think we can answer the questions in the chat as well.
Sounds great.
Right. So I'm going to walk you through. I'm also going to share my screen, but the instructions are also on Philip's GitHub repo. Actually, let me post the anchored link. So the first link you need to go to is, let me just share my screen. Right. So if you're on Philip's GitHub account and in this workshop GitHub repo, this is how you access the AWS accounts. And the first link you need to go to is this dashboard.eventengine.run/login. So I'm going to click that, open it in a new tab. Also going to post that link. Oh yeah, Philip posted it already. And what you need here is an event hash that Philip, have you already shared it or?
No, let me quickly share. So we have, since we are that many people, we have 2 event hashes. So first come, first serve, try one out. And if you are lucky, the one work. If not, you need to use the other one.
Yeah, exactly. So I'm going to take this first event hash. And what you do is you just paste it in here. And then you accept the terms and the login. And then you can sign in different ways. We recommend the email one-time password. So if you click that, you need to provide your email address. So here I'm just going to use my email address and passcode. And it should take only a few seconds until you receive that one-time password in your email.
Heiko, we have people saying event not running.
Oh, is that right? That's right. I forgot to click a button. Yes. 1 second.
Okay, we can see good now, so it should work. If not, please send a message with whatever issue you have. Perfect, works, nice.
Okay, nice. So now I got my one-time password in the email. So with that, I can sign in. And you will then see team assets not ready yet. Okay, maybe that one is already booked out. In that case, I'm going to exit the event. I'm going to use the second hash. You should see the event name. And then you can click on AWS console up here. And then open AWS console. And that should bring you in. Okay. Of course.
Was anyone already successful to get to the AWS console? In the dashboard, okay, yes, okay. Me, yes, console, I can access it. Okay, that's good.
Okay, so the only person who can't access it is the, the AWS person. Excellent. Well, good to hear that people can access it. If you can access it already, let me then just scroll down here. What you then do is you can either find SageMaker in the recently visited services, or you can just type it in the search bar up there. Just type in SageMaker, and then that will provide a link. And once you are in SageMaker, in the SageMaker overview, you can click on Notebook and then on Notebook Instances. If you at that point stop there, do not follow the steps 9, 10, and 11, because those would create new notebook instances. But what you should see in your accounts, that there are already 4 notebook instances ready for you. Now, because we're such a large group, we put 2 people on one AWS account. And the way this works now is, I wish I could log in now. Let me try again. The idea being that there's 4 notebook instances, and you have not really a way to communicate or coordinate with each other. So that means you will have to open one of those notebook instances and see if a kernel session is already running. I think I have screenshots actually.
Okay, we have people having an arrow with the same arrow. Please verify your hash code and try it again. Maybe you could. What browser are you using? Maybe it's try to use an incognito Chrome tab to really don't have any local storage cookies or whatever running. And then for which of the 4 notebooks to open. So like I said, since we are a pretty large group, we are sharing AWS accounts. So you can select one of the notebooks, first come, first serve. And when you are in Jupyter, there's the tab with running. And if you see that the notebook you opened is already running, you can easily select another one, or just kernel not running, what kernel to use. We are going to use the Conda Python 3 kernel, but I will show you everything in a second.
So yeah, you can I opened it here up in Jupyter Lab. I took some screenshots. If you see already kernel session running, then just use a different notebook instance. And then if you see nothing running, then just open up the relevant notebook, which is labs. You go into workshop 4, distillation and acceleration, and then you open up lab 3, AWS Inferentia Inference. And then I used this kernel, but Python 3, like Philip said, also works. And that's it.
I think, Louis, you can check if your training is done. And while taking a look, we are trying to figure out to help anyone who cannot access their AWS account yet.
Yeah, I will.
Sure. So let's have a look on our SageMaker job. What's happening? Okay, so we see that the job is completed. And if we then visit our model on the hub, we've now got a nice model card which tells us, okay, this is a fine-tuned version of this model on this data set, and this is the performance we got. So you can see that here we've managed to get an accuracy of around 95%, which, if you remember, the teacher had an accuracy of 97%. So we've only really lost 2% here. And MiniLM is much, much smaller than BERT-large. I can't remember, it's like a factor of 10-ish, roughly. Maybe Philip can correct me.
Yeah, it's around 10 times smaller than the BERT-large model.
Exactly. So once that model is now being uploaded to the hub, you've also got it available in a S3 bucket on AWS. And so what you can also do is you can deploy an endpoint using the same Hugging Face estimator object. And this will then basically create an endpoint where you can send requests and it will generate predictions. But since we're kind of tight on time, I'm not going to go through this. You can just run through this yourself. But it's basically just a couple of lines of code. And then you'll be able to see through these logs, what kind of latencies this distilled model is going to typically get. So shall we switch over now to Inferentia, Philip?
Yeah, just one more information. So I managed to now log in with the second event hash. So what happens is when you use the first event hash and try to log in, then you're already somehow logged in into the AWS account. So if you get that error that you saw earlier when I screen shared, you need to log out of this, like log out with your credentials from AWS at all. That's on the top right. There's a log out button. And then just open again the AWS console from this screen here. Oh, you can't see my screen right now. But just try to open it again, and then I managed to get into the AWS management console. Hope that works.
Perfect. So let's use the last remaining 20 minutes to quickly compile our model to Inferentia and run some awesome predictions. So what we are going to do, or what you need to do to convert your transformer models to Inferentia, is to use AWS Neuron Sdk, which is an SDK created and maintained by AWS to compile models, which can then be run on AWS Inferentia. And AWS Neuron is, I would say, high level, kind of similar to what TorchScript is doing. So you have your PyTorch model, and for TensorFlow, it's of course different, but like staying with PyTorch, you have your PyTorch model, and you are tracing it, like creating a static graph from your neural network. And compared to TorchScript, what Neuron is doing is not using the operations which are in the official PyTorch library. AWS has created custom operations which are specifically optimized for the AWS Inferentia chip, which means they are more efficient and more faster, which helps us to achieve the super low latency. And to begin, you can like select your kernel. I use the Conda PyTorch Pi36 kernel. And the first thing we need to do is to install Torch Neuron and some additional dependencies like transformers, datasets, and SageMaker, just to make sure that we have everything installed. This could take some minutes and time, but it should be installed afterwards. And David, yeah, it's similar to Onyx, but not, I mean, it's an accelerator, but yes, it's like creating custom or applying custom operations. Okay. I hope the installation won't take forever. Can you zoom in a bit? Yes, I can zoom in a bit. Okay. Yes, Matti, so you can, instead of what we are doing is compiling our model inside the notebook instance with AWS Neuron, but you could also use SageMaker Neo to create a compilation job and apply as instance type target Inferentia.
And Cole asks, does this work for any Hugging Face model?
Sadly, not yet. So as mentioned, Torch Neuron and the AWS Neuron SDK created custom operations for specific, basically neural network operations. And if you use a model which has implemented operations which aren't yet supported in Torch Neuron, it could be possible that you cannot convert yet to AWS Neuron. And Adolfo, yes, it's definitely suitable for any real-time use cases you have. Well, that's nice. Then we can retry the installation. So if you have seen an installation issue with datasets, remove it for now and then reinstall later. That could be possible due to some, like, I don't know, update we have released lately. But we have installed our Neuron. We can execute or define our model ID. This is basically the same model Luis has distilled in his training, but we have done it in advance. So we are already able to use it and convert it. And what we are then going to do is basically using transformers with the from pre-trained method to load our model. We apply TorchScript true, which helps us to easier convert our model. We create a dummy input, say that we want to head it later to 128 sequence lengths. So similar to TorchScript, AWS Neuron is not supporting dynamic shapes, meaning the inputs you are providing to the model always need to be the shape which you are tracing to, meaning we are tracing now to 128. When using inference later, we also need to make sure that the inputs we are providing to the model have the same shape. And then we are tokenizing our inputs to create our embeddings. And then we only need to run torch.neuron.trace, provide our Hugging Face transformer model, our inputs, and that's basically it. And then we will compile it. And at the end, we will save it to a directory with our tokenizer and our configuration to make sure we can run inference later.
There's a question from NC about how does like inference on Inferentia compare to things like inference on TPUs with respect to latency and throughput?
So I have no numbers in head how fast transformers are on TPUs for inference, but what we are doing on Inferentia and what you can do in the notebook is we are compiling a MiniLM model, which is around 150 megabytes, and I'm not sure how many million parameters. And we are achieving 5 to 6 millisecond latency for 128 sequence length per Inferentia core. Okay, so yeah, when running it, the model, you can see that's printing out some configurations saying, okay, how much of our operations can be fused and optimized. We are almost close to 100%, which is good, meaning that Inferentia will later use the optimized operations to run our inference. And still, yeah, taking some time, maybe there's more questions. Yes, so Marty is asked if it should work for other tasks than sequence classification, our example, like question answering. Yes, so it is not depending on the task. You only need to make sure that you load the model correctly with the correct auto model class from transformers and to provide the correct input. For question answering, it's of course different to what we have with sequence classification. Okay, here we can see which operations are compiled and applied, and yeah, it's done. So we have now compiled our model, and we can take a look. It's now, instead of 150 megabytes before, it's only 108 megabytes, since we are not only changing the operations inside the model, we are also converting the float 32 weights to float 16, which decreases a little bit the size with some trade-off in terms of performance. And then what next we need to do to run our model later on SageMaker is to create an inference Py script. In this case, we need to provide a model function and a predict function. This later acts as entry point for our requests we are sending to SageMaker. The model function is basically the function called when starting our endpoint, which in this case loads our tokenizer, loads the model, similar to what it's done with TorchScript. It's basically identical, but we are importing Torch Neuron instead of TorchScript, and then loading our configuration for our labels to create nice outputs and returning it to the handler, which is run behind the scenes. And then we have the predict function, which is used every time we send a request to our model, which first gets our data, and then basically the output of our model function, which is our model tokenizer and model config. And then the only thing we need to do is to get our inputs, tokenize the inputs to the sequence length. In this case, we saved it in our model config earlier to 128, run our model, run our embeddings through the model, apply a softmax at the end to basically get the highest probability, and then basically create a nice return using PyTorch utilities to get the index of our label so we can read it and what the score of it was. And after we have created our inference Py, we can run the same configuration as Lewis has showed earlier to make sure we have the right IAM permission and the right S3 bucket in our session to share with SageMaker, okay, what are we going to do? And then basically the last step we need to do, since we are this time not deploying from S3 or from the Hugging Face hub, we have our model currently stored locally in a temp directory with our code, our inference Py. our tokenizer, our configuration JSON, and the model weights. What we then need to do is to create a model archive, which contains all of those files and upload it to S3. And then we can use this artifact S3 URI later in our creation. And this can be created not in the notebook. You could also like create it on your local machine, push it to S3, and then deploy the model.
Just a question, Philip, from Dogpeel, who says, can you do like batch inference in this setup with Neuron and Inferentia? And, you know, do you get kind of good performance as well?
Yes, so you can definitely do batch inference, but you need to be careful on how to trace the model. So currently we have created our model or traced our model with an expected batch size of 1. So if you want to do batching, you need to make sure that you are tracing it correctly. And I think since the latest or the second latest release of AWS Neuron, it also supports dynamic batching, meaning you can either have a batch size of 1 or of 6 and having like an small time waiting between like the inference coming in to get a better performance or usability basically for your model. But in terms of what the throughput is, I can only refer to the blog post shared earlier. Maybe Louis, you can share the blog post again, or Gadi, if I saw you also in the workshop listening to it, maybe share what performance results AWS has already achieved with Inferentia.
There's another question from Galina about when you do this with torch.nograd, does that speed up the prediction process, or maybe why are you doing that?
Yeah, we are doing that just to let our model know that we are not calculating any back propagations, which definitely you should. I mean, the output is different, and I'm not sure if it accelerates the inference. Do you know?
I'm not sure about inference, but it definitely uses less memory. So maybe that helps.
Yeah, Raj also said it saves memory. And so while we are answering the questions, I already run the cell, which is similar to the estimator we have seen earlier, which in this case is a model, again, where we define our storage of our model and which transformers version and PyTorch version, as well as the Python version we want to use. And then we can run the .deploy method where we define on which instance and which instance type we want to use. And when this cell is finished, our model is deployed to SageMaker on an Inferentia instance, and we can start running some predictions. And I also have seen that Tiana Bay has asked the question, if we have large documents much longer than the max length, what we can do? Are you asking about the max length we have defined with 128? This length can be increased to the max length of the model. In our case, it should be 512. And if you have like still the documents are longer than this, you have to like split them up into either multiple documents, or you can like test if maybe the first 512 tokens are enough to achieve good performance, or if like the end is more important than the beginning. But you can like split it up or just experiment which are the parts most important in it. Are there more questions?
Louis, I saw a question a while back, which went back to the distillation, which I found interesting. I think it was from Sidand, if I just can find it again. But it was basically saying the performance was still good, but he saw the confidence of the student model drop. So, you know, while it's still quite accurate, it seems to be less confident about that.
Yeah, I think that's kind of it might be. I would say it's kind of expected a little bit, because the student will generally not mimic the teacher identically. Because I mean, I suppose if you wanted to improve the confidence of the student, you could try increasing this alpha parameter, which is basically the signal from the teacher. And so if the teacher has a certain confidence distribution for the classes, then increasing the signal from the teacher will then typically bias the student to get better at that. So that would be one way to try that. So increase the alpha parameter. But it's a subtle question because it's actually like a two-dimensional problem. You've got temperature as well. So it's kind of like you could try, for example, setting the temperature to 1 and then just cranking up alpha. That would probably be the way to bias it the most.
Another question now, whether the student can have better accuracy than the teacher.
So in practice, yes, for reasons I don't really understand. So there's a famous example in the Distilled BERT paper. They distilled a small BERT architecture from BERT, and then they took that model and they then, which was basically a pre-trained kind of a transformer, and then they did this kind of distillation like we did today on Squad. So they basically took, again, a distilled BERT model and distilled it on Squad. And they found that it got better performance than just training from scratch on Squad. And they don't explain it. And then I saw it in the book. We encountered the same phenomenon. And I couldn't find a good answer for this, except maybe it's a question of like, you should really do lots of like repeated runs of like training with distillation. And then maybe it's like, just a fluctuation in your metrics. But yeah, it's a funny phenomenon I've seen, and I don't know the answer.
And while you were talking and answering the questions, our model got deployed, and we can now run a request to our model. In this case, it's some movie review basically, and predicted the OOS class. Next, the notebook has basically a snippet which we could use to evaluate our model against the data set, since we compiled it to Neuron, which is cool, and we see a response, but we don't know yet how good it performs. And for this, we need to install the datasets library. You can now install it if you run into the issue, same as I. In the beginning, it's, I guess, some Python incompatibility issue. So you can try to install datasets at the end again. And what we are doing is basically using the datasets library, loading as metric accuracy as we have done in our fine-tuning and knowledge distillation steps, loading our dataset, and then creating a helper method which basically sends a request to our endpoint with the validation data point and returns the accuracy of it or the label. And then at the end, after we run all of the requests, we are calculating the accuracy for our results from our neuron model against the ground truth from our data set. And as you can see, while I was talking, we have sent over 3,000 requests to our model and achieved an accuracy from 93.899%, which is pretty good. Therefore, that we went from almost 100 milliseconds latency, I think 79 milliseconds on the MiniLM model, down to only a few milliseconds on the AWS Inferentia. And we can also take a look at a model. We included a print statement which will point you to the CloudWatch logs and metrics where where SageMaker basically stores our inference. And if we wait a few more seconds, we should see way more data points than just the one we have here. Yes, and maybe to summarize it again, since we don't have much time, we went from taking a look at the image. We have our P99 latency, which is one forward pass through the model for a 128 sequence length. And we have the accuracy, And the size of the dot basically represents the model size. And as you can see, the BERT-large model achieved the best accuracy with 97 something and is super big and has around 300 milliseconds of latency. Then we distilled it into the MiniLM model, which achieves 94% accuracy and is already way smaller. And then we compiled it to AWS Neuron and Inferentia, which got even more smaller and more faster. And then you basically get the 52x improvement in terms of latency by only losing 3% of accuracy, which is a pretty good trade-off for basically gaining the performance, and especially for real-world use cases or real-time use cases where you might not be able to wait 300 milliseconds. This kind of techniques can really help you going into production. And I think a question I've seen earlier, I'm not sure if we have answered it, somebody asked the performance of the MiniLM model just fine-tuning on the data set. And it is almost as good as the knowledge distillation part, but I think it's something around 92%, so 2% less than what we achieved with the knowledge distillation part, which is, I think, a fair trade-off. And we gained 2% using knowledge distillation and lost 0.1%, which is still 1.8% higher than the normal fine-tuning, and gained 13 times more performance with our model. So we traded basically more compute to knowledge distill our model to gain a small percentage of accuracy, but at the end we gained 13 times more latency, or lower latency basically. Okay. Yeah, thanks everyone for chiming in. If we haven't answered your question and you're super curious, feel free to open it in the forum again. We are more than happy to answer all upcoming questions about knowledge distillation or AWS and SageMaker. And thanks for joining in, and we will upload the session to YouTube. And yeah, the labs are for some times after the event available. I think it's like 30 minutes or something. You can like still play around with it.
Yes, thank you, everyone, and thanks for these awesome questions. It was a really cool interactive session.
Thanks, everyone.
Bye.
Bye.